Hello, everybody. Welcome to this new session where we're going to be looking at the constraints and basically how we take them into account. For those who are joining us for the first time, if you're just arriving, welcome. We are right in the middle of our design sessions, our live design sessions, designing this space mission and this satellite in front of the whole world for missions 237, where we are building pocket cubes that are going to help to train the maximum number of Africans and other people from other parts of the world. And we'll use this mission not only as a training platform, but to do actual useful work. This is a data relay satellite, what you would call a store and forward space mission. It collects data from sensors on the ground and then forwards this data onto a ground station. The idea is to be able to facilitate the advancement of solutions for our day-to-day, somewhat what people call basic problems, health, around energy, around infrastructure, and so on and so forth, right? Around agriculture and pollution monitoring and things like this, disaster management. So this is a bit of a context. Again, if you're just joining us, welcome. Today is the second session of the live design. The first session, we sort of set the stage. I told you about what is the NMD Association. I told you about what is Mission 237. And I told you about what we are trying to achieve, both by training and by space mission. Today, we're getting into some fun stuff, right? Don't be intimidated by the screen you're seeing. I am going to translate this into a very simple language. Today, we're looking at the mission. Again, there's the mission, and then there's the satellite. So you'll design, in a typical setting, you will design both sort of concurrently, where you design the mission, you design the satellite that is supposed to accomplish that mission. You see if the satellite is actually accomplishing the mission, and then you come back, So right now we're first looking at the mission to see some orbital constraints, where are we sending this satellite? Why are we sending it there? What are the constraints that limits the choices of what we can do, where we can send it, right? So what you're looking at is a user interface of a software called SIMU-CIC. SIMU-CIC is developed by the Centre National d'Études Spatiales, CNES, which is the French space agency. In fact, all the tools we are going to be using here are developed by the French Space Agency and are made available to just about anyone. And if you want to learn how to do what we are doing, you can learn it. If you become a member of the NMD Association, then you already have access to this particular content, right? You can learn how to do what we're doing here free of charge you become a member, and then all the training, everything becomes available to you free of charge. And the design files, so the files of the design of this orbit and the files of the design of the satellite and the document that I showed you in the last live will be available to you all free of charge, to all the members free of charge, right? We're designing it like this, like we say in French, a mondo vision. But you may be interested, okay, can I have that file? Yes, you can. And when we're done with the hardware, the design will make it available for who wants, right? It's a pocket cube. For the most part, these designs exist. There are many of them that exist. We're going to work on ours and also make it available for anyone to benefit from it, because there's a major training angle to it. A lot of members of the community will be participating, will be contributing to the mission. And we already have some roles attributed, like I mentioned last time. Please join, register for your membership in the NMD Association. Your registration will help to fund what we're doing and will give you access to just about all the good stuff we're cooking here, okay? So let's dive into it. 5 minutes in, I think we're good to go. So if you're just joining us now, once again, welcome. This is Missions 237 live design session number 2. And today we're looking at the mission constraints. So what is this mission supposed to be? And I have something fun here that I like a lot. It's a Rubik's Cube. Something very interesting about this is that this is the actual size, real world size of what we are building. This is, it's not going to be bigger than this. It is potentially going to be smaller, but I don't think so. This is it. This is the size. If you've ever held a Rubik's Cube, this is the size, okay? And hello, Paul. Ah, Paul Ebodé, comment tu vas? Ça fait longtemps. Bonsoir, il n'y a pas de version française. Alors, oui, on peut le faire en français aussi. On peut le faire en français aussi. Par contre, les membres de l'association ont cet avantage que nous, du spatial, nous qui sommes du domaine du spatial, nous savons très bien, et ça c'est intéressant parce qu'il y a une composante de cette première mission 237 qui se focalise sur l'Afrique francophone. Pas forcément dans le sens de tout faire en français, parce qu'il faut être honnête, celui qui s'intéresse au spatial doit comprendre que l'univers du spatial parle anglais. Alors, ce qu'on a fait à l'association NMD, c'est de négocier des remises sur les formations et les examens TOEFL pour tous ceux qui doivent faire monter leur niveau en anglais. Tous ceux qui doivent faire monter leur niveau en anglais, on a négocié une remise assez intéressante en partenariat avec JFN Language Center pour que tous les membres de l'association qui veulent rehausser leur niveau en anglais puissent faire se former, faire la formation au TOEFL et passer l'examen TOEFL. C'est vrai, il y a différents niveaux, mais même si c'est le plus bas, c'est déjà un niveau qui permet d'avoir assez de compétences en anglais pour s'en sortir dans le spatial. La réalité brutale d'aujourd'hui, c'est que celui qui veut s'exprimer dans l'univers du spatial ne peut pas s'en sortir sans un niveau minimum d'anglais. C'est pour ça qu'on fait ce focus sur l'Afrique francophone, pas forcément pour tout faire en français, mais pour encourager ces talents de l'Afrique francophone. Et il y a des monstres de talents en Afrique francophone à se rapprocher assez de la langue anglaise pour pouvoir participer au secteur spatial. Croyez-moi, on utilise les outils de l'Agence spatiale française, mais quand les Français s'asseyent pour parler de mission spatiale, c'est en anglais. C'est en anglais. Et c'est la vérité. On va avoir peut-être des réunions en français. Quand on plonge dans le technique, on passe en anglais. J'y ai été, j'ai fait pas mal de missions spatiales. C'est vraiment un phénomène intéressant. On est assis, tous on parle français, mais quand on commence à plonger dans les techniques pour pouvoir s'en sortir, le jargon technique commence à entrer en anglais et éventuellement autour de la table, on commence à parler anglais. Quand on finit les sessions de travail, on peut repasser au français, etc. Donc, on ne peut... Et après, il faut mentionner que c'est quelque chose de collaboratif. Il y a généralement plusieurs pays, plusieurs cultures impliquées dans une mission spatiale. Là, on est dans mission 237, par exemple. We have people from Ethiopia, Senegal, Ghana, Nigeria, Cameroon, South Africa, who are following Mission 237. And many of them will participate, even technically. Donc, il n'y a pas moyen d'échapper à l'anglais si on s'intéresse au spatial. C'est pour ça que d'entrée de jeu, on se dit, tous les membres de l'association qui n'ont pas encore un bon niveau en anglais, il faut qu'on puisse négocier une remise pour encourager leur montée en niveau en anglais. Donc, moi, je t'encourage, prends ton membership, souscris rejoins l'association pour bénéficier, de tous les contenus de formation, etc., gratuitement. Ensuite, pour bénéficier aussi des remises sur la formation en anglais. It's very important. So as I was saying, the Rubik's Cube that I hold here is the real size of a pocket cube. So the satellite we're going to design has this size, literally. And I'm holding this thing, and I'm tempted to start solving it now, but I need to not be distracted. And I want to give a shout out to a special somebody, you know yourself. If I point to Rubik's Cube and I say hello to somebody, and then the person knows themselves. So, hi. What you can do with something of this size, a satellite of this size, is what we're going to be, working on. The thing that collects data from sensors on the ground and then relays this data over has this size. We will design and build one, okay, in this space mission. But it needs to be at a certain altitude. Il faut qu'on envoie ça à une certaine altitude, It needs to have a certain mass constraints. It has to weigh a certain, its weight has to be within a certain range. And it needs to be out of orbit after a certain time. Okay, so it has a time span to do its mission. It has a time span to do what it is sent to orbit to do. And the other thing you need to know is we are not building only one. We will be building a lot of these pocket cubes, all right, to have a constellation. People will learn how to design as we design, how to build, assemble, integrate, and test as we do that, how to operate as we operate, okay? So what are these constraints? Let's start defining it. I think by now, those who were not there are there. Paul is here. I'm glad to see Paul again. He was part of a cohort some time ago when we were doing trainings. Glad you're back. So let's dive right in. This is SimuCIC. Again, I will be telling the story of what I'm doing in a vocabulary that is easy to grasp, okay? Don't be intimidated by the tools. You can learn how to use these tools. Just join the association. All the content of how to use it will be made available to you. You learn, and I personally follow through with the tutorials, the exercises. When you do your exercises, I follow and I correct and rectify here and there and make sure you get the proficiency that you need to be able to use the tools. Okay. First thing we're going to do is we are going to load the file. I showed you this file last time during the live. I created the file and I made it available, M2371. This is it. This is our mission design file that will be used on SimuCIC. Okay, this is it. As you can see, well, I hope you can see. I'm sure you can see the authors and then the association, Mission 237 number 1. We are looking at first quarter 2027. We can get this done before. And to be honest, if if we all, bring in our efforts, we can build this satellite in 3 months, inside of 3 months, and launch it. The launch part has some admin that can make it take a bit longer, but as you will see, there are opportunities among which we can choose the better one. So I've already sort of filled this in, not to spend too much time, but I'll tell you what it is about, okay? With this tool, you get to configure how your orbital constraints and run a simulation and see what happens, okay? We want to make sure that this satellite flies over enough of Central Africa as often as possible to collect data from sensors in Central Africa. Yes, we can make it a global and have a fully polar orbit, but we will make some choices around where the problems we have are most concentrated, okay? So let's look at the orbit. State vector. If you want to understand what is here, semi-major axis, eccentricity, inclination, etc., again, there is a course. It's available. If you're part of the association, you go in and you just learn, right? All of this stuff is there. This stuff is there. So, in simple terms, semi-major axis back. I think we're getting back. Just hang in there. Let's just take it out and bring it in. Okay. Let's just make sure everyone can see what I'm doing. Okay. Good, we're still there. Sorry about this. This is part of the problems that we need to solve, in our beloved continent, these connectivity issues. But we're back. There you go. As I was saying before we got interrupted by some network wahala, semi-major axis is just one way to say how high above the surface of the Earth, if this is the surface of the Earth, how high above the surface of the Earth do we need to be? But this one says, okay, how far away from the center of the Earth do we need to be? Altitude above the center of the Earth, semi-major axis, how far from the center of the Earth? Bottom line, how high does the satellite need to be? This big number here corresponds to approximately 400 and how many? 400 and some kilometers. And we made a choice. We made a choice to place this satellite in the orbit of the International Space Station. And why did we make this choice? Just make sure why did we make this choice? Because the ISS has many opportunities for people to to launch. There are many CubeSat Pocket Cubes that launch via the ISS. For a nonprofit like the NMD Association, it can cost way less to launch via the ISS, the International Space Station. So the financial cost, is a motivator to use the International Space Station orbit at its 415, I think it's 415 kilometers altitude, okay? Secondly, the mission itself, first, it's a low enough altitude that you you can have a LoRa relay that works well at that altitude. You can easily is always relative, no? But your sensors on the ground can send data 415 kilometers away above, upwards. It's a matter of design, of course. When you design it right, there's the link budget. We're going to look at the link budget and all these details when we dive into the spacecraft design itself, around the communication part, right? But you can establish a link. You can send data from your sensors to your satellite at that altitude using the LoRa protocol, okay? And you can send data from the satellite down to the Earth, also over LoRa, at 415 kilometers. So that is good. The altitude is low enough that we can safely say we will have a link, communication link, at a low cost, low power, because with a small thing like this, covered with solar panels, there's only so much power you have on it. You need to manage it right. We will see that as we're designing the satellite in the coming sessions. Then, the duration of the mission. Without orbit correction, at 415 kilometers altitude, a spacecraft like this one, not literally the Rubik's Cube I'm holding, but of this size, or not really the size, honestly. The truth is, it does matter for drag, but when it's relatively small, it doesn't make big enough difference. But at that altitude, the satellite would spend roughly 18 months maximum in orbit, which is fantastic. For the purposes of space debris, we don't want things to be hanging up in space for too long. So you're going to have about between 9 and 18 months, depending on a couple of parameters, right? So you have these advantages. It is much less cost because so many things are established already that we just need to plug in to have our satellite in orbit if we're going to use a launch via the ISS. The orbit is low enough for our link. So we're going to have our LoRa link so we can actually perform the mission. The orbit is low enough that our satellite will be out of orbit very quickly. Well, quickly, it's relative, of course, but 9 to 18 months for a space mission, if you know that the intention is to be sending more and more satellites, and if you know that no one satellite will spend more than 18 months in orbit, that is actually a good thing. It's a good thing, right? So for these reasons, so we're looking now at the mass constraint, financial constraints, link communication constraints, and so on and so forth. Regulatory constraints. We're using a LoRa protocol, well-regulated, well-known, very few constraints, very few tapes that would stop us from doing what we want to do. And there is heritage for such missions. So, as I was saying, we have that is why we chose this semi-major axis corresponding to the altitude, because we want to be closer to that orbit. Eccentricity has to do with how circular the orbit is. 0 means a circular orbit. This is fine for our simulation because the actual eccentricity of the International Space Station is 0.00 something. It's very close to 0. And inclination, this is lower than your polar orbit inclination of 98 or something degrees, or around that figure. And it brings us closer to having more passes in closer to Central Africa and therefore closer to Cameroon. Right. So this is the definition of some of these orbital parameters. Then, again, like I said, if you want to have a better understanding of what this means, how to get about these numbers, there's a free training accessible to all NMD Association members. Join, learn, participate. Yeah, that's what we're trying to do. We're trying to train people. In terms of attitude, well, I won't spend too much time here. Local orbital frame, spacecraft. We're taking the CubeSat form to have this shape, okay? The size, we'll have the actual size when we're designing the spacecraft, but we take this shape. We don't have much constraints. I define a ground station in Douala, somewhere in Douala, right? And I set the ground station there. How did I do that? I took a point, a longitude and latitude in Douala somewhere. It can be anywhere, really. As we design, we can now start fine-tuning. Those who accept to participate in the mission, we then create the real ground stations. It's not complicated ground stations, honestly, for the purposes of this mission. And we can have some of them in many different places. So I just picked a point in Douala as a starting point. And as we discuss with people and someone says, they don't have to be in Cameroon. If someone in Kenya says, hey, I'd like to support the mission I'll put a ground station here to support the mission, we will add that point as the ground station and keep refining the model, the simulation of the mission, okay? So as a starting point, I just pick a point in Douala and there we go. There. So we define a number of these parameters. Again, like I said, if you want to learn how to define these things, you can learn the content is available in the association. I'll go with the simulation and run it. Let's run this simulation. So you'll see in Scilab, this is the simulation running. What are we simulating actually? We're simulating 1 day. We're running 1 day in orbit and at the 30-second steps. So we're calculating from hour 0 to hour 24. Every 30 seconds, we make a calculation to see what is happening to the mission, okay? Right, we did the simulation. It went rather quickly. It can be much slower if the mission is complex. This is not a complex mission. Now let's look at the results. First thing we're going to look at some plots. Now, we want to see the ground tracks first. Let's take a look at the ground track. There you go. So here is the ground tracks, how it appears. So first thing we observe, if you look at, okay, all these lines are trajectory lines. So each line corresponds to where the satellite passed, right? Each line corresponds to where the satellite passed, either downwards or upwards, okay? We're going to take a look as we do a bit of a simulation animating it, right? You'll see just now. So what do we observe here? I hope we can zoom this in. Yes, we are zooming it in. What do we observe here? We see Africa. All of Africa is covered. Beautiful, because it means we can place any sensor, LoRa compatible sensor, anywhere in Africa, and it works out. Great. We observe that our ground station can be accessible within this radius. There are parameters to define this circle. It can be bigger, can be smaller, but these for UHF communication over LoRa is realistic. And with this, observe that, as we said, these lines correspond to where the satellite has passed, okay? It means that we could send data to the ground, because once the satellite passes within this circle, it is visible to the ground station, and therefore it can send data to the ground. Bear in mind that you can have similar circles around every sensor on the ground for capability to send data to the satellite. And believe you me, you will not miss one, right? You can have data over the continent every day. So inside this circle, let's look at lines in each direction. You have this one line, second line, third line, which means there were 3 passes. I'm not sure if that's upwards or downwards. I think these are downward passes. And then you have 1, 2, 3 upwards passes. If I'm mixing them around, then it doesn't matter. They are passes. It means the satellite can send data to the ground 6 times in a day. 6 times. That is good. If we had a polar orbit, it might be 2, and you don't always know that the 2 passes will be good passes. But here, you have 6 times. Are they all good passes? It's relative. That is something that is sorted at what we call the data budget. When you do the data budget, you get a sense of how long is a good pass, okay? But these are things we're going to define as we design the satellite. Now, we said at the beginning that we want to have many passes over Central Africa. We do have many passes over all of Africa. We can make it more narrower if we reduce the inclination more, but let's stick with the ISS and see the maximum we can get from it. So this is the first visual we can have after the simulation to analyze. We can also look at, the other thing I want us to look at is the visibility chronogram by duration. Just so that you get a sense of how often the satellite gets access to the ground station. We saw 6 lines. Here are the 6 lines. Corresponds to different durations of visibility. So basically, this sort of confirms what we're saying, but it also tells you at what time of the day the satellite is visible. So let's just make this such that people can actually see the time axis. So basically, this means from hour 0 to hour 24, you can anticipate when the data will be sent to the ground. So your ground station knows when it will be receiving data, around just after the first hour, just before the 3rd hour, just the mid between the 4th and the 5th hour, and so on and so forth, right? You get a sense of at what time. Of course, you can be more precise than this. This is just to get the first view, to make sure your mission makes sense. Okay, so I won't go, for this particular session, I won't go beyond this. I just want to do one more thing, which is to start VTS Broker, with the hope that we get a bit of a visualization of the mission as it unfolds in orbit, right? I need to make sure that you see all the screens that appear. They're not all showing on, let me move them. I have 2 screens here, so let me move them. Now, don't mind this satellite shape. That's not the shape. Whatever, the shape doesn't actually really matter at this point. What is interesting is, because when we do finish designing our satellite, we will replace this placeholder. It's a placeholder. We'll replace this placeholder with our design satellite. Right now, what I'm interested in is, let's see how it moves in orbit, okay? So I won't spend too much time on this view. This is the view that I'm going to zoom in a little bit more, Okay, we will get back to the other view when we would have designed the satellite. So this is the view we are interested in. Actually, let me make this a bit of a fuller screen. Voila. As you can see here, let's try and zoom this thing in. You see we put a station somewhere in Douala. This is it. Let's zoom back out. And I'm going to speed up this simulation a little bit. Because, why? Because, well, because then we get to see the satellite moving a bit quicker. In real life, the satellite is not moving this fast. You know, do you see it? Here it is. So those ones left to right were actually upwards orbits. Okay. And you see the next time it comes around, it flies directly over the station and so on and so forth. If I accelerate, if I exaggerate the speed even more, you'll see that you'll see a shadow moving, right? That is the night, daytime, nighttime, over the day. That is literally how the night is not moving, but places where it is night at different times of 24 hours, right? And you can see we're finishing 24 hours up here. And you see, where is the satellite going? Where is it, over which part of the world is it flying at what time? And you can see when it is flying over Africa, over Cameroon in particular, if that is interesting. And so we're going to fine tune. So this I wanted to show you this after this first simulation of our mission. I wanted you to see this to get a sense of what happens when you put in some orbital constraints motivated by some orbital parameters, motivated by some constraints, some real world constraints. Because in our ecosystem, it is much cheaper, much faster to benefit from a launch via the International Space Station. But if tomorrow someone calls me and says, "Hey, we're going to give you a free launch on our launcher, and these are the orbital parameters where we can set you up," we're coming back here and we're seeing if this works out for us at that altitude, at that inclination. Do we get the link? Do we actually have a mission? And we'll do simulations and calculations and make sure that it works. Okay. Let me not end with, on a. There you go. This is a more interesting screen to end on because why not? You know, let's put this back here. Let's run our very ridiculously fast forwarded simulation. And while it is unfolding, I'm going to thank you very much for your time and involvement in this live session. I will see you next week for the next design session that will be announced, and after that I'll see you for the next and for the next. And if you want to learn how to do this, if you want to participate, if you want to join our mission, there is this WhatsApp number. Just drop a WhatsApp there. Last time, actually, there was a problem because there was a typo with the in the WhatsApp number. Apologies for that. Some people reached out to us and said that it's not working, and we figured out we actually had a typo. We fixed it. This number that is rolling now actually works. You want to join the mission? Drop a WhatsApp there. We'll make it happen. Thanks again very much for your participation. We spent 40 very interesting minutes together. Until next time, keep well, stay healthy, and see you very, very soon. Bye-bye. If I can get around to actually closing this, there you go.